So in this lesson, we're going to be looking at finding range of a function. 1.2, the lesson that we had just done, we had done domain, finding domain, and we found domain algebraically, and then writing it in interval notation. And today we're going to be looking at range, but finding range, we're going to be looking at range in this section. We're going to be looking at range graphically, and then we're going to be looking at our table to verify it, to make sure that our interpretation of the graph is accurate. So first of all, knowing that we have our range and our function, just reiterating, range, we're going to be looking at it graphically and then verifying it numerically by looking at the table. Okay, so making sure that that is clear. So you will need to have your graphing calculator close by and handy. So the first function that we have is 3x minus 1, and you should recognize that this is a linear function as it is in the form of y equals mx plus b. And so we will take our calculator, turning our calculator on, going to our y equals, clearing out any equation that we might have, any function that we might have in there, and we will then type in our 3x minus 1. We will graph that, making sure that it is accurate, that we do have a linear function, and we do. So in order to determine range, there's going to be three questions that we're going to ask ourselves to look at range graphically. We're going to ask ourselves three questions. The first question is, does this part, any part of the graph, lie below the x-axis? And so if you notice, we have our x-axis that divides this graph into two sections. And so below the x-axis are all our negative y values. Above the x-axis are all our positive y values. So that's why we're going to first say, is part of the graph below the x-axis? The answer is yes. So therefore I know that I will have negative values for this function. Does part of the graph lie above the x-axis? The answer to that is yes. So I know that there will be positive values as part of our function. Then we ask, does it cross the x-axis? And visually we can say yes, it does cross the x-axis. So by looking at this, visually looking at this graph, we can say that it satisfies below, above, and crossing the x-axis. So therefore we can confidently say that this has a range of all real numbers. And we represent all real numbers using the negative infinity, infinity with our interval notation. Let's verify that looking at our table. So we go to second graph to get to the table. And we see by just scrolling up on the x value, if I look at my y values, I can see that I have negatives. So that would satisfy my negative infinity. We can see that when x is 0, my y value is negative 1. But when x goes to 1, my y value goes to a positive 2. So when I notice that on my table I go from a negative to a positive, we can make an assumption that that somehow would have to cross the x-axis to go from a negative y to a positive y. The only way to get there is through crossing over the x-axis, unless of course we do have an asymptote, but the graph does not support any type of an asymptote as it looks linear. So then I go on and I see that I have all positive values, so therefore I have all real numbers for my range. And if I want to satisfy this, looking at domain, I ask myself the questions that we looked at in the previous lesson. Does this function f of x have any restrictions? Does it have a square root? No. Does it have a variable in the denominator? Well, considering there is no denominator with a variable, the answer is no. So therefore, I also have all real numbers for my domain. G of x. So we bring our calculator back. We go back to y equals. We clear out the equation that we originally had, and we will enter x squared. We will graph that knowing that we should have a quadratic, therefore a parabola is visible. Recognizing that in the range, looking at it graphically, I'm going to ask myself three questions. Does any part of this graph lie below the x-axis? The answer is no. So therefore I will not have any y values that are negative. Does any part of the graph lie above the x-axis? The answer is yes, so I do have the positives. Does this graph cross the x-axis? Well, not so much cross, but it does look a little suspicious that it does touch the x-axis. Let's go to our table to verify. And I look at where x is 0, and I see y is also 0. So I do see that it does touch the x-axis at 0, 0, at the origin. There's all my positive values for y, and I can go back and forth, and you will see that there are no negatives that I have visible on the table as well, and the graph does support that. So I will say that with the range, 0 is included in my solution. So I have a bracket 0, and it goes up to positive infinity. And looking at the graph, I go from 0 to positive infinity on my y values for my range. My domain, again, does not have any restrictions. It does not have a radical, and it does not have a variable in the denominator. So again, the domain is sitting with all real numbers. M of x. Bringing my calculator back, clearing that out, 1 divided by x, and I graph that function, and it looks a little suspicious. I have a split function here. There's some assumptions that we're going to make until we get further into our lesson down the road this year, but as I look at it, I'm going to stick with the 3 questions I asked. Does any of this graph look like it's hanging down in below the x-axis? The answer is yes. This piece right here is below the x-axis. Part of the function above the x-axis? Yes, this piece right here lies above the x-axis. Does this graph anywhere look like it crosses the x-axis? That's going to be the assumption that we make, that this piece here is approaching but never touching that x-axis, as is the left, approaching but never touching. We call that our x-axis. We call that an asymptote that is created there. And as I said, we will be exploring that algebraically, being able to confirm that algebraically as we move in later into the lesson. But for right now, we're going to make that assumption. But let's go to our table, and let's see what the table has to say. Well, there we have our negatives. That's verified that we do have negative values on the y. But if we see 0 for x, we do have an error. And it does look like we have our positives going back into our negatives. And if you see that that is gradually approaching 0, but as far as I go on my calculator, I will never reach 0. So I think it's a fair assumption to say that that graph created asymptotes going off to the either side. So as we go through, it does not cross the x-axis, so therefore 0 is not included in our solution. So for the range, I had negative values, did not cross the x-axis, so 0 is not included, but I pick back up again and I continue on with positive values. So that's how I represent my negative of the underneath the y-axis, underneath the x-axis, above the x-axis, did not cross the x-axis itself. We had asymptotes there. Algebraically, looking at the domain, I do have a variable in the denominator, so therefore I know that x cannot equal 0. We saw that very clearly on our table, where when x was 0, I had an error message for my y. So therefore I cannot put I cannot put 0 in to that function as x, because it would result in an error for the y. It would cause that function to not work properly, so therefore I cannot use 0 as part of my input. I represent that just like I will represent it as I did with the range. Negative infinity to 0, a break, 0 to infinity. And because 0 is not included in the solution set, I'm using parentheses, and again, infinity symbols are always represented with the parentheses. Moving on to h of x, going back to y, clearing out and typing in that function, but understanding that in the denominator, should I have more than one term, we need to represent that denominator using parentheses. So I'm doing a divided by 3x minus 1, and I graph that. Again, I have a graph that looks a little suspicious. We might have to make some assumptions, such as, again, having an asymptote at the x-axis, and it looks like we might have an asymptote vertically as well, but we'll see that when we look at our domain. But this graph approaching the x-axis but never touching, again, we will verify that using our table. But right now, my 3 questions that I'm going to ask: do I have part of the graph below the x-axis? Yes. Part of the graph above the x-axis? Yes. Does not seem to cross the x-axis? No. Verifying that with my table, and I can go and I see that I'm going to be getting smaller and smaller with my y values as x is getting smaller. My y values are also getting smaller, but they will never approach or never reach 0. So therefore that does say that I'm going to be approaching the x-axis but never actually crossing or touching the x-axis. So the range for h of x will just look identical to the range of m of x, where I have my negative values that lie below the x-axis. I do not cross the x-axis, so I represent that with a 0, non-inclusive, and I have values above, or part of the graph above the x-axis, which represents the positive. Domain, it does look like I have an exclusion, a restriction, so I say that 3x minus 1 cannot be 0, therefore x cannot be 1/3. So I bring my graph back in, and it's not the y-axis that's creating the asymptote, it is actually where x is 1/3 on the graph right here. So I represent that as negative infinity to 1/3 union with 1/3 to infinity. Domain. N of x. We're just going to bring that over on top of the x minus 2. And again, bringing back the calculator, my y equals, clearing out my previous function, square root x minus 2. And that is underneath the radical, so I need to make sure that I go to the right with my cursor to make sure that plus 5 is outside of that radical. I go to my graph, and I might think that my calculator is not acting up correctly as the whole graph is not there. Well, whenever you have a radical, a square root in your function, you will get a really funny looking graph that we have here. This is very familiar to a square root. So I look at that. Is any part of this graph, looking at range, any part of that graph below the x-axis? The answer is no. Any part of it above the x-axis? Yes, but not all of it. So we'll have to look at that. Does this graph at any place cross the x-axis? That is no. So with that no negative, no 0, where does it look like this graph happens to start? Well, it looks like possibly at 5. Let's double check that going to our table. So I go to where my x is 0. There's x is 0. And if you notice in the y, all of the errors, that represents all the negatives that it did not occur. And here I have not x at 0, but x at 2. I have my 5. So that will be my starting point for my range. So it's going to go 5 is included, and that's my range. So it's 5 on to infinity. As you can see with the y values, they do increase, getting bigger and bigger, kind of slow, but that is the typical for a square root, starting at when x is 0. And if you wonder, is that maybe 4.99? You can verify that by just plugging in a 4.99 here, and what you'll see is that that actually does not create that graph. The graph does actually start when x is 2 and y is 5. So I have my 5. And looking at my domain algebraically, I know that x minus 2 has to be greater than or equal to 0. It has to be positive. So therefore x has to be greater than or equal to 2. and I represent that with 2 to infinity. And again, the table there supports that the only time that I have y values that are valid is when I start when x is 2. That is finding range graphically and verifying it using the table. And we also filled in with the domain, looking at that algebraically.